Hello everyone. In the previous video, we studied sequences. Now, we move on important step further and talk about infinite series. A sequence is simply an ordered list of numbers. For example, 1, 1/2, 1/3, 1/4, and so on. Or another sequence like 2, 4, 8, 16, and so on. The main question for sequences is, does the sequence approach a finite number when n becomes very large? Now a series is formed when we add the terms of a sequence together. We write first term plus second term plus third term and continue forever. And in compact mathematical notation, we say sigma from n equal to 1 to infinity of a sub n. The main question now becomes, does this infinite sum approach a finite value? There are two possible behavior. First, a convergence series. This means the partial sums approach a finite number. For example, 1 plus 1/2 plus 1/4 plus 1/8 and so on approaches 2. Second, a divergence series. This means the partial sums do not approach a finite number. For example, 1 plus 1 plus 1 plus 1 and so on clearly grows without bound. For many infinite series, calculating the exact sum is very difficult or even impossible. So mathematicians developed a special tool called convergence tests. These tests help us determine whether a series converges or diverges without finding the exact sum. The first convergence test we study is called the divergence test. It is also called the n-term test. The key idea is very important. If a series converges, then its individual terms must approach 0. It means limit of a sub n as n goes to infinity must equal 0. The divergence test says if the limit of the terms is not 0, then the series must diverge. But there is an important warning. If the limit equals 0, this test tells us nothing. The series may converge or it may still diverge. For example, the harmonic series diverges even though the terms themselves approach 0. So the divergence test is very useful because sometimes we can decide very quickly that a series diverges. Now let us study one of the most important type of series. This is called a geometric series. A geometric series has the form shown using sigma notation. Here, A is the first term and R is called the common ratio. A geometric series converges only when the absolute value of R is less than 1. If the series converges, its sum is first term over 1 minus common ratio. But if the absolute value of r is greater than or equal to 1, then the series diverges. In example 2, we want to determine whether this series converges. In this example, the common ratio is 1/2. Since the absolute value of 1/2 is less than 1, the series converges. And as you see, its sum equals 2. Geometric series are very important because many other convergence tests compare unknown series to geometric series. Now we study the comparison test. The idea is simple. We compare a difficult series with another series whose behavior we already know. This test is especially useful for positive term series and rational expressions. Suppose we have two series with terms a sub n and b sub n. If a sub n is between 0 and b sub n, then we can compare their behavior. If the larger series converges, then the smaller series must also converge. And if the smaller series diverges, then the larger series must also diverge. In example 3, we want to determine whether this series converges. Notice that the term of this series is less than 1 over n squared. And we already know that the series 1 over n squared converges. Therefore, by the comparison test, the original series also converges. So, the comparison test allows us to use known series to understand more complicated ones. A p-series has the form 1 over n to the power of p. There is a very important convergence rule. If p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. For example, the harmonic series is the sum of 1 over n. This is a p-series with p equal to 1. Therefore, the harmonic series diverges. This result is very famous in calculus. Even though the terms become smaller and smaller, the infinite sum still grows without bound. The integral test creates a connection between infinite series and improper integrals. Suppose the term of the series comes from a function f of x, and suppose the function is positive, continuous, and decreasing. Then the series and improper integral behave the same way. They either both converge or both diverge. In example 4, instead of studying the series directly, we examine the improper integral from 1 to infinity of 1 over x dx. After solving this integral, you see that the logarithm grows without bound. Therefore, the improper integral diverges. And because the integral diverges, the harmonic series also diverges. The integral test is very powerful because it connects series with ideas from calculus. The ratio test compares consecutive terms of a series. It is especially useful for factorial, exponential expressions, and power series. We define the quantity L using the ratio of consecutive terms. Then we interpret the value of L. If L less than 1, the series converges. If L is greater than 1 or infinity, the series diverges. And if L equal to 1, the ratio test cannot decide. Example 5. We want to determine whether this series converges. After simplifying the ratio of consecutive terms, we obtain n plus 1 over 2. Then we take the limit. The limit becomes infinity. Since L greater than 1, the series diverges. In example 6, again we compute the ratio of consecutive terms. The ratio simplifies to 1 over n plus 1. Then we take the limit. This time the limit equals 0. Since L is less than 1, the series converges. These examples show how powerful the ratio test can be. Infinite series are not just abstract mathematical ideas. They appear in many important areas of science and engineering. In physics, infinite series are used in wave equations and quantum mechanics. In engineering, they appear in signal analysis and electrical circuits. In numerical methods, computers use infinite series to approximate complicated functions. So, convergence tests are not only theoretical tools, they are also very important in real-world applications. In the next videos, we will continue studying more advanced topics related to infinite series. Thank you very much for watching this video. If you find this video helpful, please like the video, subscribe to the channel, and share the video with others.